Hello. So here we are back virtual again. So we're going to do this in a different format now. I think we're going to just use the whiteboard here for the time being. I don't know that it's going to be worth setting up the other glass board if we're just going to do this for 3 weeks. If I get the feeling that we're going to go longer, then I'll do that. I'm using Screencastify here, and I'm just using my Chromebook to record this video. So hopefully this works. And if this doesn't work and you guys say this stinks, I'll try to come up with some other plans. So what we're going to learn about here is, so we're kind of done with our study of derivatives temporarily. We learned the product rule, we learned the chain rule, we learned the quotient rule, we learned all that, how to find derivatives. We know what the derivative means. It's how to find the instantaneous rate of change of a function. It's how to find the slope of the tangent. We know all that stuff. We've learned then spent some bunch of time using finding applications of derivatives. We did some related rates problems. We did L'Hopital's rule. We did maxes and mins. The derivatives can tell us a lot about how the function behaves, max, mins, inflection points, all that sort of thing. So our introduction to derivatives is sort of over. And now we're going to go the other way and talk about what we call antiderivatives. So to motivate this, I'm going to say, suppose we know f prime of x, okay? And so I'm going to say we know f prime of x, and I'm going to say that f prime of x is equal to 3x squared plus 2x plus 4, okay? And now I'm asking you, well, this is the derivative. What's the function? So can you tell me what would f of x be? Okay, if that's the derivative, what's the function? Okay, so I'm looking for a function here whose derivative is equal to 3x squared plus 2x plus 4. Okay, that's what I'm looking for. And I think if you just sort of think about this backwards, you might say that, well, f of x would be x cubed plus x squared plus 4x. Okay, and if you're not sure how I got that, don't worry about that right now, but just verify it. I mean, is the derivative of this right here that? And the answer is yes, it is, okay? But I would argue here that there's an entire family of functions whose derivative is equal to 3x squared plus 2x plus 4. Because I could say, what if I added 3 onto the end of that? Would the derivative of this still be that? The answer is yes. What if I said, what if f of x is equal to x cubed plus x squared plus 4x plus 7? Would the derivative of this still be that? Yeah. What if I said f of x equals x cubed plus x squared plus 4x plus pi? Would the derivative of this still equal that? And the answer is yes, it would. Okay. So it turns out that there's a whole family of functions whose derivative is equal to what we said. And the way we represent that family is we just put a plus c here, okay? We call this the constant of integration, okay? Now, I've all of a sudden introduced a new term here, integration. Are we talking about integration here? Well, sort of, yeah. We'll get to that in a second, okay? So the deal is essentially, what if we know the rate of change? Can we go backwards and find the function? That's the question, okay? So let's just sort of generalize this form here and get out of this example here. So let's make sure you guys can still see that. Okay, this is called an antiderivative. Okay, and it's also called an indefinite integral. And you'll see why it's called that in a second. Okay, so the general form of an antiderivative, aka indefinite integral, is this. Let big F prime equal little f. Okay? If this is true, we say that big F is an antiderivative of little f. Okay? And realistically, big F plus c is an antiderivative. All right? So now, if we go back to this example that we just were talking about here, okay? The big F in this problem was x cubed plus x squared plus 4x plus c. It's the function whose derivative was equal to 3x squared plus 2x plus 4. Okay? Does that make sense? Well, you can't hear me. I'm standing in my room with a bunch of empty desks. Hopefully that makes sense. Yeah. All right, I'm going to pause just for a second. So I just wanted to erase the board and get a clean slate here, literally. So now we got a clean board. I'm going to introduce some notation for us. So notation for antiderivatives. Okay? So this is where we're going to introduce this new symbol, okay? So the way that you read this, okay, so here we've introduced this new symbol here, which is a funny looking S, okay, it's an elongated S, okay, the way that you read this is you say the indefinite integral of little f of x with respect to x, okay? Or the antiderivative of f with respect to x. Either way. Okay? It's either the indefinite integral with respect to x or the antiderivative of little f with respect to x, okay? Now, I'm adding on this with respect to x thing, okay? And where that's coming from is right here, okay? This dx here, for right now, I'm going to just tell you that that means with respect to x. It's like we're anti-differentiating with respect to x, just like we derivatated with respect to x, okay? So same idea right now. Now, later on, when we get into definite integrals and we actually learn about what integration really is, this dx is going to take on a whole new meaning, okay? So right now, just kind of think of it as with respect to x, okay? And then we're saying it's equal to some other function plus our constant of integration, okay? That's how we're going to typically denote antiderivatives, all right? Is with this symbol. What makes this integral indefinite is that there are no numbers here. Eventually, you're going to see things that look like this. Okay, where we'll have numbers on these. Those of you that are in physics, you might already have experienced that. But we're not there yet, okay? So that's called a definite integral. These are called indefinite integrals, all right? So right now, we're just going to do some kind of examples to kind of get you thinking, basically just to get you thinking backwards. I mean, that's really what we're doing here. We're just going backwards from using the rules that we learned back in September. We're just going to do these backwards, okay? So like the power rule, we're going to go backwards. The quotient rule, maybe not. The chain rule, we're going to go backwards. Product rule, we're going to go backwards. We're going to learn how to do all these differentiation techniques that we learned. We're going to learn those backwards, okay? So here we go. Let's just get out some examples here. So here we go. This is going to be an antiderivative, 3x squared plus 2x plus 4. Okay, this actually I think is the example that we just did. Okay. Now, technically speaking, there should be parentheses around this. Okay. The whole thing. Sometimes you'll see people get lazy and they won't put the parentheses around that, and it'll just be written like that. I'm not going to make a big stink about it. So there you go. So the answer, we're saying, okay, what function has a derivative that's equal to 3x squared plus 2x plus 4? Okay, and we already know that was x cubed plus x squared plus 4x plus some constant. Okay? So you might be asking yourself, how did you get that? How did you go backwards? Okay? Well, I looked at this one and I said, well, 3x squared, I know that's x cubed. I mean, I know the function when I take the derivative of x cubed, I get 3x squared. 2x, I know how to do that. I said, okay, well, if I have x squared, I know to take the derivative of that and I get 2x. And if I have a constant 4, what function would have a derivative that's equal to a constant 4? Oh, a linear function, 4x, okay? And then there's my constant of integration, okay? Now, if you notice right out of the gate here, the antiderivative of a sum is the sum of the antiderivative. So, you know, the rule about derivatives, the derivative of a sum is the sum of the derivatives. The same works for antiderivatives. So we can do this one piece at a time, okay? Let's do another one. How about this? The antiderivative of sine of x. Now, there's a glare on the board right there, which I'm trying to eliminate. I've taken half of the light bulbs out of my lights. I might jump back there after I record this video and try to get these other ones. There's a glare there I see, and a glare over there I see. So I'm going to try to work on that. Try to make this as good of an experience for you as possible, because this experience, you know, doing the best we can here. So what are we looking for here? We're looking for a function whose derivative is equal to sine of x. What function has a derivative that's equal to sine of x? And you might think cosine. Might be wrong, because it's not positive cosine. It's not regular cosine. It's negative cosine plus c. Now, why is the antiderivative of sine negative cosine? Because the derivative of negative cosine is sine. That's why. Okay. Let's do one more over here before we erase the board. So you're going to practice probably like I did, writing integral symbols, and you'll get really good at it. It's what you should do when you have, you know, just some downtime, like on Wednesdays or early in the morning when you're sleeping in instead of sleeping in. What function has a derivative that's equal to e to the x? That's what this is asking. What function has a derivative that's equal to e to the x? And you're like, oh, Mr. Ritter, I know that. It's e to the x plus a constant. Okay, plus constant. A lot of times, I'm sure I'll do it in one of these videos. A lot of times I refer to this constant as chips. Plus chips, okay? Because I love chips. There's only one type of chip that I can't stand, that's salt and vinegar. But any other type of chip, I am a chipaholic. I can knock off a bag of chips in one sitting with no problem. It's kind of like an addiction I have. It's a problem, really. All right, let's pause and erase. Okay, we're back. Clean board. Oh, not clean board. That's offensive right there. All right, here we go. So another example. So I have the antiderivative of natural log of x. What function has a derivative that's equal to the natural log of x? Now, you might be sitting there thinking it's 1 over x, but that's not right. Because the derivative of natural log of x is 1 over x. Okay? The derivative of natural log of x is 1 over x. I'm looking for a function whose derivative is natural log of x, the other way around. At this point, kids, you don't know this. Those are question marks. Okay? You don't know this. You don't know the answer to that. Okay? Maybe if you have some sort of photographic memory, you might remember from one of the videos way, way back when we first learned the product rule, you might remember the answer to this was this, x ln of x minus x, okay? But there's no way that you would have known that. There's no way to know how to do this, okay? In fact, how we come up with this answer takes some serious work that we won't even learn until second semester, okay? So for all intents and purposes right now, we don't know the answer to this, okay? But if you did take the derivative of this function right here, you're going to get natural log, okay? In fact, I think you had to do it on a quiz too at one point. But where this came from, I mean, this is as far as you know, I pulled this out of the sky, okay? So right now, we don't know the answer to that necessarily, okay? Or at least we don't know where it came from. All right, so let's try another. How about this? So we're looking for a function whose derivative is equal to secant squared. What function's derivative is equal to secant squared? And of course, you're thinking, I know that. It's tangent of x plus chips, okay? The function whose derivative is secant squared is tangent, okay? But do you know the other way? Do you know the antiderivative of tangent? Do you know what that is right now? Do you know a function whose derivative is equal to tangent of x? I don't think you do. I don't think you do right now. Okay? Because in order to do this problem, it requires a technique that we haven't learned yet. Maybe you remember. Maybe I doubt you do. I'd just keel over right now if somebody said, "Oh, the answer to that is the natural log of secant of x." Okay? I highly doubt you remember that. But you could verify that. Is the derivative of natural log of secant equal to tangent? Let's just check real quick. If I took the derivative of the natural log of secant of x, what am I going to get? Well, I'm going to get 1 over secant of x times the derivative of the inside, secant of x, tangent of x. Those guys cancel, and well, all be. Okay, look at that. So the derivative of that is equal to tangent, but you don't know where that came from. Okay, so I'm not expecting at this moment right now that you would know that. Okay, not all of these antiderivatives you're going to know right now. Okay. In fact, like I said, we're going to learn a whole bunch of techniques on how to find these antiderivatives, okay? Right now, we're just working off functions that we sort of know and easy polynomials, okay? Speaking of easy polynomials, what if we do one more and then see if we can come up with some sort of rule? How about this? X cubed plus 7x squared plus 2x plus 3. What's the antiderivative of that? Okay? What's the antiderivative of that? Well, we're going to do this one at a time, term by term here. I need a function whose derivative is x cubed. What would that be? A function whose derivative is x cubed. Well, it's going to be x to the fourth, right? Something x to the fourth But if the derivative of x to the fourth isn't x cubed, it's 4x cubed. So how would we undo that? What if I divided that by 4? Now if I took the derivative of this, I'm going to get 4x cubed over 4, and those 4's will cancel, and you'll be left with x cubed. Okay? Plus 7x cubed over 3 plus x squared plus 3x plus chips. Okay, let's talk about where I got this. Where did that 7x cubed over 3 come from? Well, I started with 7x squared, right? I need to anti-differentiate that. Well, if I'm starting with x squared and I'm going to go backwards, it's going to be a cube, right? But again, the derivative of x cubed is 3x squared. I need it to be 7x squared. So what do? I divide by 3, okay? So there we go. So like, could we generalize this dividing by thing? So let's call this like the anti-power rule. Remember the power rule for derivatives? The power rule for derivatives was the derivative of x to the n was n x to the n minus 1. So what if we go backwards? The anti-power rule. What's the antiderivative of x to the n? Well, it's x to the n plus 1 divided by n plus 1 plus chips, okay? And then if you've got a constant out in front, like this 7 here, that 7 just hangs there, right there. You see that? That's 7x squared. That 7 just hangs there, so I have x cubed over 3. Okay, so 7x cubed over 3. Some people might write this, by the way, as like 7/3 x cubed. Yes, that's fine. No big deal, okay? Let's try some more, but I'm going to pause so I can erase. All right. So let's try one more using this anti-power rule. Let's do 3x. Well, let's do this. How about 3 over x squared plus 2 over x cubed plus 7x. Okay. Let's do that one first. Now, before we do this one, this is what many of you should have done on your test. When I asked you to take the derivative of something like this, you probably should have rewritten that as 3x to the negative 2 plus 2x to the negative 3 plus 7x. It always helps to do a little algebra or a little rewriting before you do the calculus. Okay? And so now we're going to do the anti-power rule. We're going to say, all right, we're going to do this right here first. 3x to the negative 2. I add 1 to the exponent. Negative 2 plus 1 is negative 1 divided by negative 1. Plus, well, I add 1 to the exponent. Negative 3 plus 1 is negative 2 divided by negative 2. And that power rule actually works here, guys. 7x to the first, add 1 to the exponent, and divide by that exponent. And then I don't forget the chips. Okay, so there's the answer. Ugly looking, but if we want to clean it up, it would be negative 3 over x plus negative 1 over x squared plus 7x squared over 2 plus chips. Okay. How about this? What's the antiderivative of 1 over x? What function has a derivative that's equal to 1 over x? Natural log of x plus chips. Okay? And by the way, typically when we anti-differentiate 1 over x, we put this, the x inside the natural log, we put that in absolute value. Maybe at some point I'll show you an algebraic reason of why we do that, but right now you could just think of, we do that because the natural log of a negative number does not exist, because e to no power will give you a negative number. All right, let's look at one that looks really, really difficult. That looks really, really scary and really blurry inside that glare, but that's the antiderivative of 1 over the square root of 1 minus x squared. We're looking for a function whose derivative is equal to 1 over the square root of 1 minus x squared. And what is it? It's inverse sine. Okay? So it really helps if you know your derivative rules in order to do antiderivative rules. Go figure, okay? Speaking of those rules, if you look at page 491 in your book, okay, I'm going to double check that real fast. I'm glad I checked. It's page 489. Page 489 in your book. Okay? There's a big table, okay? If you look at page 489, there's a big table of derivatives on one side and antiderivatives on the other side, okay? You probably want to look at that and make sure that you know all of those. You should know all the derivatives already, so you should be able to know, then go backwards and know the antiderivatives, okay? So you make sure you take a look at that. All right, let's pause and erase. So next thing we're going to do here is we're going to solve what we call an initial value problem. Okay, we're going to solve what we call an initial value problem. If you remember back in the day, at the very beginning of all this, I said if you really want to know what calculus is all about, if you really dig into the guts of calculus, it's all about point and slope. Where you are right now and how fast are you changing, okay? Or how fast are you changing and where are you right now? Okay, putting those things together, okay? So here's an example of where that's true. So I'm going to say, suppose that f prime of x equals x cubed plus 2x. And f of 0 equals 4. Okay? So notice what I've given you. I've given you how fast we're changing and a value, a point. Okay? Where are you right now and how fast are you changing? Okay? Point, slope. All right? So now my task for us is, given these two bits of information, I want you to find f of x. Okay? So some of you might be saying, that point is going to help me identify what the constant of integration is, or what the chips are. And you're exactly right. Okay? So here we go. So in order to do this, the first step is to find the antiderivative. So we're going to anti-differentiate. Yes, that's a verb. We're going to anti-differentiate x cubed plus 2x. And I'm going to say, okay, that's x to the 4th over 4 plus x squared plus chips. Okay? But now I'm going to take this nugget of information and I'm going to say, okay, f of 0 equals 4. So f of 0 equals 4. So 4 has to equal 0 to the 4th over 4 plus 0 squared plus chips. Okay, and now I'm going to solve that for the chips. So that's 0, that's 0. So 4 equals the chips. Okay, and so now my particular solution here, my specific f, the member of the family. Remember I said this was a family of antiderivatives? Now with this particular point that we're going through, we're saying, hey, there's one specific member of the family, and it's this member right here. It's x to the 4th over 4, I'll get out of the way, plus x squared plus 4. When I put the chips on the end there. Okay? So this is what we call a particular member of that family of antiderivatives. Okay? It only works because we went through that point. We said, all right, We know our derivative. We know a point. Here's our function. Okay. Let's do one more example like this. I'm going to pause though. Oh, sorry, we're back. So one more example of an initial value problem. So suppose f prime of x equals sine of x plus 2x, and f of pi equals 0. Okay? So I'm giving you a slope, essentially, and a point. And I'm asking you to find f of x. Okay? So what are we going to do? We're going to anti-differentiate first. Okay? So I know the antiderivative of sine. Let's see, it's negative cosine. And the antiderivative of 2x is x squared. And then I'll add the chips in for the constant of integration. Okay? And then I'm saying f of pi equals 0. So 0 has to equal negative cosine of pi plus pi squared plus chips. Okay, so 0, now we have to solve this equation for c. 0 equals, the cosine of pi is -1, negative is +1, pi squared is just pi squared, plus chips. So what are the chips? Well, the chips are equal to -1 minus pi squared. Okay, and I purposefully chose this as an example because a lot of times students want to just see like this initial condition here, f of pi equals 0, and assume whatever value right here is the value of c. And that's not always the case. That was the case in the first example that we did, but it's not always the case in fact, most of the time it's not the case. Okay, you actually need to set it up and go through the algebra. Okay, so what's our final answer here for our mother function, if you will? It's negative cosine of x plus x squared plus, I guess, -1 minus pi squared. And I'll just put it in parentheses like that. That's the chips right there. Okay? So what have we learned? We've learned the anti-power rule. We've learned what an antiderivative is. We learned what a family of antiderivatives are. We learned how to sort of work backwards. If I give you the function, you can anti-differentiate and go backwards and find the function whose derivative was that. Let's see, what else we learned. We learned how to solve an initial value problem. What's an initial value problem? It's when I give you the derivative and a point, and you work backwards to find the original function. Okay. So there's a lot packed into this 30 minutes, 33 minutes and 27 seconds to be exact. The problems that you're going to work on from the textbook for this are in section 410. It's 465 to 501. Do the odd ones from that. And then 521 to 524. Do all those. Those are some true false. Those are some conceptual problems. See if you can think about this concept conceptually. So that's the end of this video. Man, it was fun seeing you guys for 2 weeks. It's sad that it's almost December 1st and I still don't know everybody's names. It actually crushes me. It was like, I mean, that last 2 weeks during hybrid was just like a tease. And then now you're back sitting in your basements and bedrooms and just watching me ramble at a board. Give me some feedback on the videos. Let me know if this works. Yeah, we'll see you later.